So now that we have center of mass, we're going to start applying this to orbits and looking at different orbits. And we looked at universal gravitation already. We also have to tip our hat to Kepler because Newton looked at a lot of Kepler's things, and Kepler informed us a lot about how things move. We will see the first equation ever of motion in this section, and this is important as far as understanding what is directly related to what. So this is, Johannes Kepler is going to precede Newton. So he was born poor, and he studied Copernicus, who was the first person to put forth that the sun was at the center of our solar system. And then he was interested in why there were only 5 planets, because that was what you could see and why they all rotated around it at certain distances. And so he had this unusual idea that if there are 5 planets and 5 regular solids, that the orbits would each correspond to one of the solids if you put them all inside of each other. And when you did this, it turned out that for the 5 planets that we knew, he found a solar system that were very close to the distances that Copernicus calculated. So this is his original idea, that we start with a triangle and then we're putting that inside of a square, and then the outside edge would be where it actually rotated. This leads us to Bode's law. Bode's law led us to think that there was a planet X. And so the idea is that the distance from one planet to the sun, the next distance after that is going to be an increment of that, and then that increment again to there. And we're going to have this progression. The one we're missing between Mars and Jupiter is now the asteroid belt. So maybe there was one at that point. So if we look at these distances, what Bode's law tells us, we start with this sequence where we have 0, 3, 6, 12, 24. So we added 3 to here, then we added 6, then we doubled and added 12, then we doubled and added 24, then we doubled it and added 48. You can see we're doubling the distance every time. And then if you add a 4 to each of these numbers after you do this, and then divide by 10, you get this 0.4, 0.7, 1, 1.6, 2.8, 5.2. And we can see how close this actually matches up to where Mercury, Venus, Earth, Mars is, and then Jupiter, Saturn, and Uranus. The one missing in here was planet X that they looked for, and it turns out that's where the asteroid belt is. And this is a law in the sake that it's called this, and it seems to work for our planets, but that's as far as it goes. So we can look at this linearly. And it works also for moons around planets. They're also going to follow this relationship. So Kepler was really interested in data. And so he wanted to apply all of the data that he could get to the orbits to really understand what was going on with these orbits. Up to this point, it was accepted that they were circular orbits. The person who had the best data is Tycho Brahe, or Tycho Brahe. I've heard it pronounced both ways. he was the most eccentric of all scientists. And so Kepler accepted a job with him. And then when Tycho passed away, he used his data to lead to his laws. And I'll have you guys watch a short video on him because he really is out of this world crazy with pet elks, and he had a gold nose. And so we have these observations that he was able to make. And then trying to put all of this together, it didn't quite work. It didn't quite work that these were circular orbits. And so the big idea was that Kepler realized that it was elliptical. And a circle is an ellipse, but an ellipse isn't necessarily a circle. So circular motion, it turns out, is super, super special. So when we have satellites going around the Earth in circular orbits, they have the ability to adjust their speed, to make their speed precisely what it has to be just to go in a circle. Everything else that's going around, everything else is just in ellipses. So if that space station were to lose power, it would stop being in circular motion. It wouldn't be able to make adjustments. It would then be in an elliptical orbit around the Earth. So how do we get an ellipse? If you have 2 points, focus 1 and focus 2, if you stretch a string and put a pencil in there, and then you pull the string taut as you go around, you would get an ellipse. If both your focus 1 and focus 2 are at the same point, you get a circle. And that would be the most special of ellipses. And you'll see that the planets are in very close to circular orbits. So it makes sense that they thought they were in circular orbits. The more squished down it is, we call that eccentric, the eccentricity of the orbit. And so the most eccentric example that I can give you of a former planet would be Pluto. It has a very eccentric orbit. But if you think about comets that are going around the sun, they have very eccentric orbits. They go way out and it's squished way down. The longer axis, so when it's squished down, it gets wide here. The longer axis is the major axis. The shorter axis is the minor axis. If you take half of the major axis, we call that the semi-major axis, which is going to be the distance from the center to there. So his first law is that the planets will move in ellipses with the sun at one of the focus and nothing at the other. And so there will be times where the planet will be closer and then be further away as it goes around this orbit. The second law is that in equal amounts of time, equal areas are swept out. So in this time from here, that it goes here, it's actually going faster. I'll be able to explain this to you in terms of angular momentum and energy later in the year. But it's going faster here, but the area, when it's further away, it's going slower. You can imagine just the force, there's less force on it, right? And when it's slowing down, this blue area here and that blue area there are the same. The third law is the most important one, and this is the one that I think I should stop and start